Hello world, and welcome to the rocket velocity calculation that I'm going to do. We have a rocket of mass m emitting fuel at mass delta m at a velocity of v sub e, the exhaust velocity. Basically, it looks like this. The rocket is going to change its momentum by m delta v. Meanwhile, the fuel is going to be changing its momentum by delta m times v sub e. And I'm just going to put a negative sign in that because it is going the other direction. And so I'll put a little equal sign in there. And so it's m delta v equals negative v sub e delta m. The impulse delivered to the rocket is equal but opposite to the impulse delivered to the fuel. Now I could make that a lot more complicated with the initial momentum of the rocket plus the fuel over here is equal to the final momentum of the rocket plus the final momentum of the fuel. But if you did take this equation and simplify it, a bunch of stuff cancels out and you just get this. I'll show you. Taking these two terms, mv plus delta mv, equals these two terms, mv plus m delta v, plus these two terms, plus mv minus delta m v sub e. We can see that mv cancels out on both sides, and I've got a typo here, and delta mv cancels on both sides, and we're left with adding delta m v sub e to both sides. We'll have delta m v sub e equals m delta v. Now, oh noes, I broke physics. Let's see, there was a sign up here, right? Negative m v, it was all the same except I had a negative m delta m v sub e up here. What's wrong? Not quite. I didn't so much break physics, but I'm what you call confused. Actually, there are two subtle sign conventions which need to be taken carefully into account if you want to derive this formally. I could say delta m is positive when the rocket loses mass or when it gains mass, and I could also say that v sub e is positive or negative. I know that m delta v equals negative v sub e delta m is the right equation because it gives me what I want at the end. But are there two equivalent explanations for getting to it? Because the equation up here definitely does not give the negative sign. In fact, when you add delta m v sub e to both sides, you get a plus sign over there. The reason, I think, is that I'm equating two things that are not the same. I am equating the change in the mass of the rocket, which is negative, with the mass of the fuel emitted, which is positive. You can almost see my confusion in the equations themselves. Notice the presence of the uppercase delta m up here has been changed to lowercase delta little m down here. In fact, this equation, m plus delta m v equals m v plus delta m v minus v sub e, is not even right. It should be, whoops, little delta m right here, and little delta m right here, and then we would replace at the end, once we derive this with the plus delta m, we would replace delta m, delta capital M is actually negative delta little m, v sub e equals m delta v. Okay, now that I've fixed my painfully subtle sign convention error, let's do the calculus that will solve this thing. We want to turn this thing into an integral by getting everything involving the m on one side and everything involving the v on the other. So I'm going to divide by m 1 over m dm, and we'll leave that v sub e over there. Negative v sub e 1 over m dm equals dv. And then I called that the right, so I'll go ahead and write it in this form. dv equals, and you see instead of writing 1 over m here, I wrote m to the negative 1. So v sub e m to the negative 1 delta m. So now I'm going to choose appropriate limits of integration, assuming that the rocket starts from rest and with mass m sub I, and figure that it probably finishes with some velocity v final and final mass m final, which will of course be smaller than our initial mass because it is lost fuel. So this dv is just going to be integral of dv from 0 to v final is equal to, and then I'll just write v sub e because it's a constant, I'll write it outside the integral, from mass initial to mass final. I forgot my negative sign, which was so important to me. 1 over m dm. And then we will come down here and start solving this. The left-hand side is just the integral of dv is v from 0 to v final. The integral of 1 over m dm will have negative v sub e times natural log of m with mass starting at mass initial to mass final. So that will be v final minus 0 equals v sub e times the natural log of m final minus the natural log of m initial. And that is all a negative sign in there. Should have put parentheses around there. And finally, using properties of natural logs, that's going to be, since this is negative negative, that's the positive part, it'll be natural log of mass initial divided by mass final. And that will be a number greater than 1 times v sub e. One result that kind of surprises me is to get velocities greater than the exhaust velocity. V final is equal to natural log of 9d plus 10 over 10 VE. Here, for instance, at a 10 kilogram rocket with 90 kilograms of fuel would have a final velocity of 2.30 times the exhaust velocity. The rest of the math we have here is consideration of a two-stage rocket, which I started by doing incorrectly, and then I followed up by doing it correctly, or better. This is imagining if we have 99 kilograms of fuel with a 1 kilogram rocket, showing that if we do two stages, first burning 90 kilograms of fuel, then burning 9 kilograms of fuel, we get the same result as if we burn all 99 kilograms of fuel at once. For instance, if you burn 900 kilograms of fuel, then drop a 90 kilogram tank, then burn 9 more kilograms of fuel, you'll gain considerably more velocity than if you burned 909 kilograms of fuel but kept the 90 kilogram fuel tank. Well, I'm done with this interesting question for now.